So we're going to kind of tie things together with our linear relations here, and we're going to look at the ideas of variation, direct and partial, rate of change, and the first differences, which is going to be a new concept we'll introduce. If you recall, the rate of change is the rise over the run of a linear graph. So we use that little basic formula, rise over run, is m equals, I use m, and a lot of your teachers will probably use m, although I believe the textbook and some people do use other letters like k. It describes how the slope of the graph looks. So how does that slope look? How steep is it and whatnot? It'll describe that by use of a rate triangle. So in this case here, I have a rate triangle. This is the rise. This is the run. And do note that in this case, the rise would be considered negative. We always read the run from this point to this point. We always read from left to right. So because we're reading this way in the run, the rise is going down, so that's going to be a negative rise in this case. So this would be a negative slope or a negative rate of change. And the other two concepts we've discussed is direct variation, describing a linear relation that passes through the origin, and then partial variation, where that linear relation doesn't pass through the origin. In this case here, this is a partial variation because the graph does not pass through the origin. It's got to cross through this point here. This is the origin. All right, that is the origin. So if it doesn't pass through there, it's partial variation. If it does pass through there, it's direct variation. And the equations that we've used for those, with direct variation, y equals mx, m being the rate of change. So we just whatever the constant rate of change is, we multiply that by x to find the respective y value. In the case of partial variation, the difference is that we take that rate of change and multiply it by x, but we also add or subtract a b value, which will thus move this graph up or down along the y-axis here. This is the y-intercept as well. So that is also known as the y-intercept. And this is known as the slope or rate of change. So if you hear someone refer to, write it in slope y-intercept form, write a linear equation in slope y-intercept form, this is what they're talking about. The y equals the slope or rate of change times x plus or minus the y-intercept value. All right, so the new concept we want to look at now is first differences. So first differences are the change in each equal step through the dependent or y variables or values. This is the rise in the linear variations. So this is we're looking at the rise portion. So the rise is how we're moving, going back here. The rise is how we're moving vertically along the y-axis here. So we're looking at the change in the y values. So we want to find the first differences of each of these tables here and see what they are. So the first differences, and I'll just do first diff as I usually abbreviate. What we do is we find the change, well, from this to the previous value. So we got to look and make sure that our scale is constant here. So we're going up by 1 each time. That's good. And so now we can check, that'll allow us to check the step on the y. So y is going up by 2. And how do we calculate? The way we would calculate that, some people like to see it calculated. We can't calculate anything here because we don't know what's before this one. So we just cross that one out. And here we calculate this. This is 3, the current value, minus the previous value. 3 minus 1. And 3 minus 1 is 2. The next one would be 5 minus 3. The current value minus the previous value. And that is equal to 2. The next one would be 7 minus 5. The current value minus the previous value, which is 2. And then finally 9, the current value minus the previous value of 7, which is 2. So here we have these first differences. So these are the actual values of the first difference. In each case, this graph, as we step over, we're going up by 2 each time. So this is related to our rise. So our rise is consistent. We have a consistent first difference. And because the first differences are the same, this means this is a linear equation. This is a linear relationship, sorry. So if the first differences are constant, It is linear. Okay, that is important to note. Now, if we look at the next set here, we have, again, equal steps going up. We're going up by 2 each time. 2, 4, 6, 8, 10. So we're going up by 2s. That's good. So we can then determine if this is linear. And look at our first differences. Again, we can't calculate that first value, but we have negative 15 as our current value minus negative 10. Remember, when we subtract the negative, we want to change that to addition and add it. So negative 15 plus positive 10, that's going to give us negative 5. The next one would be negative 20 minus negative 15, which is the same as negative 20 plus 15. Add the opposite, and we would get again negative 5. Negative 25 minus negative 15, or sorry, minus negative 20. And so again, we're going to get negative 5, and finally negative 30 minus negative 25 is going to be negative 5. So in each of these cases, we have a consistent value of negative 5. So our first differences are constant. So this looks like it is a linear relation as well. So here we're going up and we're going positive values. Here we're going down and have negative values, but our linear relationship is still consistent. So up by 2, down by 5. In this last case here, we don't have a consistent step here. There is 1, 2, 4. So this is inconsistent. Right here, we don't consistently go up. However, these do. So this here actually breaks our possibility of this being a linear relationship. This is going to go 1, 2, and then it's going to jump up to 4, and so it's going to stagger the graph. So because these aren't constant and these are, this is not a linear relationship. So not linear because of that jump right there. Okay, it has to be a constant set of steps up. So we look at this in the terms of an example problem. So we're given a table here. So we got time and volume. Maybe we're dumping water out of the pool. And so what we want to do is calculate the first differences and then graph it. Calculate the rate of change 2 ways. I'm going to show you a separate way we haven't looked at yet at calculating rate of change. And then we're going to write an equation to represent the relationship. So looking at this table of values, we're looking for our first differences. So if we look for our first differences, we're only worried about our second column here, our dependent column. And as time goes on, it's going down each time. And we have no change in the first position, but the difference in the second one is 40 minus 45. And when we subtract 45 from 40, we're going to get negative 5. You may not need to do this portion here. You may be able to look at this. It goes down by 5, goes down by 5, goes down by 5, goes down by 5, goes down by 5. And if you can see that in your head, that is awesome. And you are welcome to skip this step of writing this out. I'm going to write it out for those of you that don't see those relationships right away. So I'm just taking this current number and subtracting the previous. This is what's called a difference. Remember, subtraction, another term, is to find the difference between two numbers. So again, we have this constant first difference of negative 5. Every time we're going down by negative 5. So we want to graph this relationship. I already set up a scale. Again, I'm using that broken graph here. That's what that little break means. So we're not consistently going up until we hit here. So 20, 25, 30, 35, 40, so on. And then my scale across the bottom is going up by 5s. So I'll plot my points. When I'm plotting, I'm not worried about the differences, just the time and volume. So time 0, I'm up here at 45. At time 10, I'm at 40. 20 and 35. 20 and 35 is right here. And then 30 and 30. 40 and 25. And then 50 and 20. So there's all my points. A nice pretty line. And I'm going to connect the dots. In this case here, I'm not going to extend the graph beyond that last point because here is where it's broken. So dropping it down, I could continue down. And if I was to have this over, it'd be at like 60 and 0. But it's not 0 and 60 because this graph is broken. It would be at 15 actually in that case if we're going down by 5s. So this here shows and illustrates our relationship as a graph. Now we want to calculate the rate of change two ways. So one way that we've covered before is that we can make a a rate triangle. So from here to here, say, I'm picking 2 points where the grid lines meet. Okay, I'm not picking right here because I don't really know exactly where that is. I know exactly where that point is. It's at 10 and 40. And this one here is at 30 and 30. So I know exactly where they are, letting me calculate the rise and run easily. So in this case, as I go left to right, I'm going down from 40 to 30. I'm going down by 10. Minus 10 is my rise. And then along the bottom here, I'm going from 10 to 30. So that is an increase of 20. So in this case here, I see that so this is method 1, using the rate triangle. I have m equals rise over run, or m equals, in this case, rise of negative 10 over positive 20, which is simplified down to negative 1/2. In method 2, we can use the table. So again, m equals rise over run. That does not change. But the rise is the change in the second column, our dependent column. It's our differences. So it's our first differences. So we've actually calculated the rise here. The rise is negative 5. It goes down by 5 each time. So it's going down by 5, down by 5. So negative 5 is my rise. And my run, I look over here at my column here and see what the change is each time. And each time it's going plus 10. Plus 10. So it's going up by 10 each time. So my run is 10, or positive 10. And again, I can simplify that down and get negative 1 over 2. Both these values are the same. My m value in both cases is negative 1/2, which it should be because these are both the same relationship and the rate of change should be the same. So that's two ways you can do it. You can use the rate triangle if you've graphed it, but if you haven't graphed it, the rise and run can be found by looking at the first differences and then the differences in the x values. So the rise is here, this is the run. Okay, so that's the run. This is the rise. Now, we want to write an equation to represent the relationship. Well, looking here, this is doesn't cross through 0, so this is a partial variation. Our partial variation equation has the y equals mx plus b values. Again, m being the rate of change or slope. B is the initial value or the y-intercept. So where does it start? And so I can look at my graph and say, okay, my b value is going to be here at 45 where it crosses the y-axis. And my rate of change we've already found is 1/2. So y equals negative 1/2 x. One of that in blue. 1/2 x plus 45. There we go. So now we can use that equation there to find any value on our that would hit our graph here. So earlier I'd mentioned that at x is 60, it should be 15, and that's why we didn't continue this graph down, because down here below that is not correct. But let's double check that. So we can use this equation here, and I'm going to sub in. So I got y equals negative 1/2 times 60 plus 45. So this will tell us what the y value should be when we hit 60, which would be over here somewhere. So negative 1/2 times 60. So negative 1 divided by 2 is going to give me negative 0.5. Negative 0.5 times 60 is going to be negative 30. Negative 30 plus 45, and that's going to give me 15. There's that y value that I had mentioned earlier. So that is differences. First differences, the variation and some rate of change all kind of put together, and some calculations you can do.